Hey everybody, so now that you guys know how to use the various graphs of concentration versus time to check for a zero order, uh, ln of a concentration versus time for a first order, or 1 over time for a second order, we can use that experimentally to run a reaction and try to calculate what is the order of a particular reactant. We could similarly use the same method that we were talking about in class with constant half-life, as well. But the thing we're going to focus on in this particular lab is looking at creating our three graphs, all right? And how we do that is we are going to figure out the molarities of substances over a course of time by measuring their absorbances, because we can't measure it directly, right? So there's a machine in the back called a colorimeter or a spectrophotometer. And fundamentally what happens is light shines through a solution that has color. And obviously the color that's in the solution is going to block or absorb some of that light. So what we can do from those is measure how much light is getting blocked in a series of solutions we set up. And that's what part one of the experiment is all about. We're going to create what we call a Beers-Lambert plot. Right? And a Beers-Lambert plot is what you see here. It links the absorbance of a substance to the molarities. Now, we can't directly measure molarities. So you're going to say, how do you create this? Well, what we do is we create a series of solutions that we know the molarities of. Right? Then what will happen is we'll measure their absorbances. Now we have this graph that links the absorbance to the molarity. So when we initiate a reaction and that molarity begins to change, what we can do is monitor the absorbance and use the graph in reverse to know what the instantaneous molarity is at that given point in time. Right, so the first part of this experiment is we have to create that Beers-Lambert plot. Right, so what we'll do is we'll set up a series of solutions with varied molarities. Those molarities you see are listed here on the bottom of the graph. We're going to create a crystal violet concentration of 2.5 micromolar, which is times 10 to the negative 6th, 5.0 times 10 to the negative 6th, 7.5 to the negative 6th, 10.0 to the negative 6th, and 12.5 to the negative 6th. Then what we'll do is we are going to dilute our stock solution of crystal violet, which is naturally purple, down to essentially lighter and lighter shades of purple, which in theory should block light less and less and less. So the first part of the experiment is calculating what those dilutions should be and creating those solutions. And so I always walk you guys through the first one in the lab to make sure we remember how to do it. And then I let you guys go on and do the others. So if you look into the crystal violet packet, which I'll share with you right now. What you'll see, all right, is crystal violet has this big, crazy structure that you see here on the bottom. All right, figure 1A and figure 1B are both the crystal violet. Notice they both carry a positive charge. And the reason we're getting two structures here is because we have resonance, right, between the crystal violet. But the take-home message here is there's a positive charge on both of these larger crystal violet dye structures. All right, the C plus carries it in one, and the N carries the plus down here in the other. And that structure, that positive ion, creates an effect that allows this substance to reflect light at the wavelength in the purple range. All right, and we're going to exploit that. Right, so if you scan down here, and we'll come back to that because that's for part two of the experiment. Right here, what we need to do is set up a series of dilutions to create those molarities that we were talking about. Right? The 2.5, the 5.0, the 7.5, and so on and so forth. All right, so if we do that first one together, you guys know a dilution is an M1V1 equals M2V2. The stock solution that I have in the back, it is 25 micromolar. All right, and you'll see all this when I take you back. So I've got an M1 of 25 micromolar. I need to figure out how much of that I need. Okay. So I need to figure out how much of that I need. I know for one of my test solutions, I want to create a 12.5 micromolar, and we're always going to create a volume of 10 milliliters total. Right? So if I set up that dilution and I solve, I'm going to get 5 milliliters for my X value. That means I need 5 milliliters of the stock solution, the 25 micromolar, which means the rest of the 10 is made up of distilled water, right? So the X tells you how much of the purple crystal violet to use, and then 10 minus the X gets you how much distilled water. All right, so the first thing you guys want to do then, right, is figure out what are those other values. Right? How much stock do I need when it's 25 micromolar X, but it's 10.0 in 10? Then it's going to be 7.5 in 10. Then it's going to be 5 in 10. Then it's going to be 2.5 in 10. And you're going to get a list of how much crystal violet stock you need and then how much water you need. All right, and then we'll go to the back and we will create. All right, so I'm going to show you the setup of that dilution, and then we'll come back up and show you how you create your Beers Lambert plot. So let me carry you guys back there. All right, so this guy right here, this is my crystal violet. Very pretty purple color. All right, and this is my 25 micromole. All right, here's my distilled water. And here are my test tubes. And here is a serological pipette. All right, and this is also a volumetric pipette. So if I bring that up nice and close, you can see that this guy measures from 0 to 10, and you have a marking every 0.1, which means I know I'm certain about the tenths, and I'm estimating the hundredths. So this is above what we need accuracy-wise to go 1 pound. So when you set up your series of dilutions, and I'll show you the first one, right, what happens is we're going to go in and we're going to get the amount of crystal violet out that I need. Right? So I go in here, right, and you take this bulb at the top, and you push down on it, and you push a bunch of air out of it. Right? That's going to allow you to create a vacuum up in here. All right, so when I push on this button here, right, it's going to draw a solution up into the pipette. And then when I hit the button here that says E for expel, I can transfer it where I want it to go. So for that first part, I want, and you guys would take a smaller sample of this, right? We wouldn't ever reach directly into the stock. But I'm going to put the tip of that in there, and I'm going to draw up my solution. Now, I overshot there, right? But that's okay. I can just gently expel till I'm at the 5, which I now am. So I'll take that out, and I'm going to transfer the 5 into here. What you guys would then do is you would measure out all of the other crystal violets, right? And the 5 milliliters is the most potent, right? Because we're diluting it. That was the 12.5 micromolar. It's going to be less and less and less and less. All right, so I'm just going to take a little bit less each time. You guys will know the exact values for these just to get you a feel for what we're looking at. So you guys would have done that and then that. And obviously you would measure these much more accurately, right? But I'm just getting you a visual here. That and that. All right, then what you would do is you would clean this guy out. Okay. So I go over here, rinse them. And then I would get the appropriate amount of water for each of these guys. Okay, so we draw that up in, and then we fill this guy with the 5 milliliters of water, and then the right amount of water for this guy. Go back in, right amount of water for this guy, the correct amount of water for this guy. and the correct amount of water for that guy. All right, and what you're going to see when you do that is you should be transitioning from the darkest colored purples down to the lightest colored purples because we're decreasing the molarity of the crystal vial. Now, we didn't initiate any sort of reaction here. We just diluted it down because we're trying to create those various concentrations. All right, then what we'll do is we would use our colorimeter, which is this guy right here. Right? It's got an open space, and I'm going to put a cuvette in here. Right? And the cuvette, all right, is going to be filled with our various solutions, and then the probe is going to measure what the absorbency is. So here's your cuvette right here. Right? And then what you would do is you would go and get your 12.5 molar. And we would transfer a bunch of it into our cuvette. And then I would cap it. Right. Then what I would do is I would get one of these guys here, which is called a chem wipe, and I'm going to wipe this cuvette down because if I have any fingerprint smudges on this cuvette, that is going to increase the absorbency, right? And it's going to make me think that the solution is more powerful than it is. Right. So then what we would do is we would take that cuvette, we would put it in there, we would close it, we would turn it on, we would monitor, we'd get an absorbency. All right, then I'd take that one out. Empty them back out. Into here. Right, and you would simply repeat the process for each of the following 5. All right, we go through that, and that's going to allow us to build our Beers-Lambert plot. So let me show you what that part's going to be like. Okay. All right, so you know that that first solution that you tested, that you created, was 12.5 micromolar. You would monitor its absorbance. And in the table, right, I will pre-fill those numbers in for you. You will know what those numbers are. All right, so we'll go in. You're going to find out that one has the highest absorbance. So you have a point. Then our second one was the 10 micromolar. You get its absorbance. It's a little bit less. Then the 7.5, it's a little bit less. The 5.0, it's a little bit less. The 2.5, it's a little bit less. And then obviously we have a point at 0.0. Right, what you've just created is a link between your absorbance and your molarity. So you're going to do a line of best fit, and you'll do all this in either Excel or Google Sheets, either Excel or Google Sheets. And now what I have is a tool, a Beers-Lambert plot that can link any absorbance to any molarity now, right? So even if I get an absorbance later in the experiment that falls out of the range of the ones that we had listed, right? Oh, here's an absorbance right here. What you do is you trace over to where you hit the line, and when you drop it down, you know it's molarity. Oh, my absorbance was here. Trace over till you hit the line. Drop down till you hit there. And that is going to allow you to say what the instantaneous concentration of one of your solutions is, even though you can't directly monitor it. So this is how a Beers-Lambert plot functions. We create it in part 1, and then we're going to use it in part 2. Right? And that's what you see here. Right? In the blue for part 2, that Beers-Lambert plot is going to allow us to determine the order of reactants, right, for the CV and for the OH negative. Now, we won't have to go through the whole process for the OH negative. We'll do it for the CV, and I'll just give you the data for the OH negative that you would need. All right, so like I said, the crystal violet is purple. So that purple vial in the back, all right, is that big crazy structure with the positive sign. Right? Now, when I react that substance with hydroxide, what happens is the hydroxide goes in and it combines with that positive ion to create something new. So here's our crystal violet, that structure. Here's the positive, there's another positive. OH negative is going to come in here and it's going to bind with that positive charge on the carbon, right, and create this structure. So you're going to say, Big Whoop, why does that matter? Well, it matters because when the positive charge is present, crystal violet is a purple colored dye. When the OH combines with it, it changes the wavelength that it absorbs and re-emits light, which means it becomes colorless. So what's happening is as the OH reacts, the purple is getting less and less and less purple, right? That's something we can monitor. We can measure how much purple there is, which is how much crystal violet's molarity is. That's what part 2 is all about. All right, so what we'll do is we'll combine the OH negative with the crystal violet. Then we'll take that cuvette, we'll put it inside, right, of the colorimeter, and we are going to live monitor what its absorbance is over a series of time, right, for 900 seconds. Like I said, for part 3, notice I've given you the first 2 columns. Okay? So you don't have to worry about that. And you're going to say, well, why didn't you give me the ln of OH or the 1 over OH? I don't have to. Those are just calculator functions. Right? And you won't have to either. So here's how you're going to generate your numbers. The colorimeter is going to tell you the absorbance. And in the one I share with you, those absorbances are all going to be filled in. That's all that's going to be filled in that table too. What you'll have to do then is take that absorbance that I give you, for instance, say the 40-second absorbance is 0.49. What would happen is you would trace up to 0.49 on your graph. And then like I did here, you'd go over, you'd go down, right? That one where I estimated it, ballparked right at the 7.5. So I could go over and say, hey, this guy's going to be 7.5 micromole. And so you use your Beers-Lambert plot to get the second column. I'll give you the absorbances. Then you just use a calculator, right? I would take the ln of 0.75, right? And if I do that in my calculator, ln 0.75, right, that value equals, right, negative 0.28. Right? And then similarly, you'll take 1 over CV concentration. So for the last column, 1 divided by 7.5 to the negative 6th. Right? And you'd get 1.3 times 10 to the 6th. Right? And if I do the ln, sorry, I'll have to do the ln again. I forgot to put the negative 6 in. Right? ln of 7.5 second e negative 6. All right, that value ended up being negative 11.8. And this is what you'll do. You'll fill in this table all the way down, right? Which is why it's nice to work on it in a shared doc in groups. You can target certain segments. Your partner can target certain segments, and you guys can merge data. Notice it's saying I don't have data points for the 0 and the 20, because don't forget, it takes me time once I initiate the reaction to cap it, to wipe off my cuvette, right? To get it in there, to let it start reacting. So that's why we don't measure our first one until 40 seconds in. All right, so you get all those filled in. And now what that is going to allow you to do is create your 3 plots that you're going to check for. Your concentration versus time plot, which would be your check for 0 order, your ln versus time plot, which would be your check for first order, and your 1 over time plot, which is your check for second order. So for part 1, the crystal violet, you're going to create 3 graphs. All right, I'm sorry, for the first part of part 2. 3 graphs for the crystal violet. Only one of those 3 will be linear. You will now know what crystal violet's exponent is. You'll repeat the procedure with the OH negative for the second part of part 2. So then you'll get 3 more graphs. So at the end of this experiment, you should have 7 graphs. Your Beers-Lambert plot, and then your 3 checks for the crystal violet and your 3 checks for the sodium hydroxide. All right. You create those, find out who's linear, and now you know what the exponent is, and you would be able to write a rate law for the reaction, because we've got rate equals K CV plus to the X, OH negative to the Y, and now we are going to figure out the X and the Y so you could write a rate law. All right, so that's the theme of the experiment. Right, hopefully all that's sinking in. Like I said, I'm not even going to take you to the back because you've seen the process already. All I would do is take a cuvette and inject some sodium hydroxide and then monitor it over time. It would be a lot of sitting and watching for numbers. You guys have those numbers. All right, so get with your partner, start rolling, and I will be around for questions.